Chapter 3 is Evaluating Properties. What are properties? You certainly know temperature and pressure. Temperature, frequently abbreviated with a T, pressure, many times with a lower P. Specific volume is identified usually as a lowercase v. Uppercase V would be volume, where we have length cubed, whereas specific volume would be a length cubed per unit mass. The internal energy, we had talked a little bit about that in our chapter 2 dealing with the first law of thermodynamics, and the internal energy would be an uppercase U or a lowercase u. If it is uppercase U, then it's a quantity of energy, shall we say kilojoules, whereas the lowercase u would be kilojoules per kilogram or unit mass. We have not talked about enthalpy yet, but enthalpy will have the symbol H, and it's actually equal to our internal energy that we have, U, plus our flow work, which is P dV. And finally, entropy. The entropy value will take on the symbol of S. We will deal with entropy in chapters 5 and 6. What I expect you to get out of chapter 3 are that you understand what is a phase, also a pure substance, and finally, the state principle. As we look at various substances, we will frequently represent them in some form of graph where we might have pressure and specific volume, or temperature and specific volume. They are used quite frequently. As I stated, we were very interested in phase, and we are interested in when do you have a phase change? When do you have a substance that is in two phases, part liquid, part vapor, for example, and what is the energy associated with each of those? Once we have the property data, we can then quantitatively do an energy balance. We will be interested to locate the various states on pressure volume, temperature enthalpy, these type of figures. So if I did have a temperature and specific volume, and I started out at atmospheric pressure, and I start to boil water. Actually, I'm not boiling it yet. It starts off initially at, let's say, 20 degrees C. So what happens? As I boil it, I'm at a certain specific volume. As I increase in temperature, the specific volume would increase as well because it would expand. Now I reach finally 100 degrees. And what happens at 100 degrees? I change phase, and that liquid water goes into vapor form. So you can imagine that the specific volume of the vapor at 100 degrees gets much, much larger. And eventually, but the temperature doesn't change. That is, once you start boiling water, you can leave that pot of water boiling on the stove, and with the thermometer in there, it doesn't change. It just stays at 100 degrees until all the water is boiled away. After that, the specific volume can increase and the temperature can increase. What we want to do is to be able to say, for this specific volume at this temperature, what are the other state variables or state properties? What are the enthalpy, the entropy, the internal energy? Knowing each of these, we can begin to do an energy balance. As soon as you have two independent properties, you can determine all other properties, and they are already tabulated. So we can go through table A1 through table A3 of the Moran textbook and take a look at any given temperature and pressure, and it would tell you what the other values are, or temperature and specific volume. Frequently, we'll be dealing with air, and air can be treated as an ideal gas for most applications that we need to work with. So how do we apply the ideal gas model for thermodynamic analysis? We need to be able to do that. We need to recognize what it is to be homogeneous. That means that the chemical composition of it and the physical structure of it need to be the same. So the homogeneity of a physical structure really means that you are all solid, such as ice, or liquid, such as liquid water, or vapor, such as steam. So in the examples provided, by your book, air is generally always in a gas phase, and we can go ahead and say that air is homogeneous. If you are drinking water and the water does contain ice cubes, then you've really got two phases. So therefore it is not homogeneous because it has two phases, liquid and solid. Similarly, a vinegar and oil salad dressing will have two different liquids, and they don't really mix well, so therefore they are separate. Most all our work in the introduction to thermodynamics will deal with pure substances only. We treat water as a pure substance. We treat air as a pure substance. We treat refrigeration fluids as pure substances. And from that, we can do a tremendous amount of energy analysis. Any two independent state properties will allow you to look up or calculate all other state properties. However, not all state properties are independent. For example, density is simply the reciprocal of specific volume. So you could not use density and specific volume as two independent parameters. Similarly, because enthalpy contains the specific volume in it, it is not necessarily an independent property. So we need to be sure that the two properties that we have are independent. Some intensive properties can be independent in a single phase, but they become dependent when there's more than one phase. An example of this would be temperature and pressure. When I am at atmospheric pressure and I start to boil, my temperature remains constant. But while that temperature is remaining constant and the pressure remains constant, the specific volume will expand as more and more of that liquid water at 100 degrees is vaporizing and turning into vapor. Therefore, on average, the specific volume will be increasing even though the temperature and the pressure have been the same. So when you have more than one phase, some parameters or properties are not independent.